Hey guys, so today we'll be covering the concept of electrical power. Electrical power is a very important concept, specifically in electrical engineering and circuit design. And power is normally always one of the specifications that we always need to design for, especially when we're looking at high voltage or high current electrical circuit boards. So, power, especially when we're, for example, buying components at a store, or even when we're buying light bulbs that we're just going to put in our own houses. Power is a very critical component of any electrical system that we must design for or always utilize. So let's take a look at what exactly electrical power is and how we can really use this concept to our advantage. So let's kind of go over what the real definition of electric power is and understand what it really entails when we're looking to really design for it. So electrical power, we normally call that as P, is the rate at which electrical energy is turned into heat, light, motion, etc. So, electrical power can really come in a variety of different ways. Electric power, for example, you see this especially um, on light bulbs for the most part. Whenever you go buy a light bulb that could be 10 watts versus 20 watts, that rating for each individual light bulb is going to specify how much of its electrical power it can turn into light energy. Specifically for an engine also has a power rating. If an engine has a greater amount of power, that engine has a greater capacity to turn actual mechanical energy into motion for a vehicle. So power can really be used for a lot of different aspects. It can be used for motion, it can be used for light, it can be used to turn heat. If you add a lot of power to food that you, for example, cook, that food is going to cook a lot quicker. So power is a rate. If we normally look at how power is defined, this would be on power is equal to the change in energy over the change in time. And this can be seen pretty pragmatically. If you, for example, let's go back to our food example. If we were to apply a lot of power or a lot of electrical heat to our food that we might cook in a microwave or on a stove, the food would cook a lot quicker, therefore the delta T would increase quite rapidly. So this is the fundamental concept behind power, and power is always something that we need to look at in not just really electricity, but in a lot of different aspects of our life. Of course, we'll be looking at power from an electrical standpoint here, and there's a couple different ways we can really define power when we look at circuits. There are three fundamental ways that we really look at power and how we really calculate power in any circuit. The three main formulas, and we always use P for our power equation, is going to be equal to V multiplied by I. Power can also be equal to I square multiplied by R. And power finally can also be equal to V square over R. Now, if we have a little understanding of how Ohm's law works, and let's do a little revision of Ohm's law. Ohm's law is the relationship between V equals IR. V, let's recall, is equal to the voltage that's applied to the circuit. I is going to be the current that actually goes through the circuit, and R is the total resistance of the entire circuit itself. Likewise, power is also dependent on these three variables, P, V, I, and R. So the first equation, for example, V is going to be equal to voltage. I will be equal to the current, and R will be equal to the resistance. Of course, we calculate voltage in terms of volts, V. Current, we calculate in terms of amps, I. And then resistance is going to be in terms of ohms. And the symbol for that is omega, or this symbol right there. So these are the three fundamental variables that we always need to know. However, why exactly is power super important? Power can be looked at a lot of different ways once again. Every time we turn on a light switch, we use electrical power and we have to pay power to our utility company. Similarly, power also governs heat generation. So whether you are in safe operation or you want to overheat, a lot of these things are dependent on power. So it really helps engineers design efficient systems and really creates a set of restraints and circumstances that we can really design electrical systems based on. So to reiterate once again, we can really look at the importance of power for energy consumption, and you could look at this as utilities that we might pay. A lot of times these are measured in kilowatt hours when we multiply the watts of power by the time it takes. And finally, we can look at the heat created in a system. Finally, what is the actual equation, or what does power really measure in? Power is going to be measured in watts, and that is normally doubling in every single equation. Continuing on, let's look at some examples and really understand how power can be looked at in any simple DC circuit. So we've got an equation here. Let's look at example one. A 12-volt battery is connected to a 6 ohm resistor. What is the power dissipated by the resistor? So in any situation similar to this, it's always helpful to draw a picture. And in this case, we'll draw a circuit diagram. So we have a 12-volt battery here, and we'll connect that to a 6 ohm resistance, and we'll call that resistance R1. We need to specifically calculate how much power is dissipated by this R1 resistor of 6 ohms. So in this case, we have three different equations to our benefit that we can really use. Let's look at them once again. We have P equals V square over R. We have P equals IV, and we have P equals I square R. In this case, we have the voltage applied to the resistance, we have V, and we also have the resistance of the circuit itself, which is going to be R, which means that when we're actually going to solve this problem, we'll use this formula right there. So let's actually plug and chug into this equation. P equals V square over R. The voltage of this this circuit is going to be 12 volts. So we have 12 square, and the resistance of the circuit is 6 ohms. This is equal to 144 over 6 ohms, which is going to be equal to 24 watts. So 24 watts of power, whether that be through heat, motion, whatever that resistance is really set up to do, 24 watts of power is going to be dissipated by that single resistance. Now, that resistance could be something like a motor, it could be something like a light bulb. So, resistances can really come in a lot of different shapes and varieties. However, we're really going to look at this as a simple DC circuit where the resistance is going to just simply dissipate 24 watts. We don't know how that 24 watts is actually going to be dissipated. Let's look at example number two and make this a little more challenging. In this case, we already have a circuit that's drawn out for us. We have a 12-volt battery and two resistances connected. We have R1, which is 4 ohms, and R2, which is 8 ohms. We need to find the power used by each resistor and the total power of the entire circuit. So again, let's write all of our equations. P is equal to V square over R. P is equal to IV, and P is equal to I square R. In this case, we need to calculate the current through each resistance first. Let's calculate that since I is going to be one of the variables that we need to still solve for. In this case, let's calculate I1. I1 will be equal to V over R1, which is going to be equal to 12 volts over 4 ohms, which will be equal to 3 amps. This is a simple Ohm's law equation. Next, if we calculate I2, this is going to be equal to 12 volts over 8 ohms, which is going to be equal to 1.5 amps. I accidentally wrote amps here, not ohms. Next, we can finally calculate the power dissipation. We want to specifically use this equation right here, P equals IV. In this case, we have both the voltage and the current. Each resistance we know, since they're in parallel, is going to have 12 volts across each one. So we already know in both equations, the V is going to be equal to the 12 volts. So let's calculate the power. P is equal to IV, which is equal to 3 amps from the first resistance multiplied by 12 volts is going to be equal to 36 watts of power dissipated by R1. Similarly, we can do something for P2. P equals IV. The current through resistor 2 is 1.5 amps multiplied by 12 volts is going to be equal to 18 watts. This is one of our answers. So 36 watts by resistance 1 and 18 watts by resistor 2. When we calculate the total power, we simply sum these values up is equal to 36 watts plus 18 watts. We get 54 total watts of power that's dissipated within this circuit. So right away, we can see that these powers are additive. And if we start stacking these resistors in parallel, we can see that there's a lot of resistance and a lot of power that we have to draw from this battery. So we always need to keep in mind how much is the battery or the voltage source or whatever you have. What is the power capacity for that battery such that we don't accidentally end up blowing it up? So let's really conclude of why we want to do this. The reasons we want to really study power are it influences device performance, and that could be through heat, motion, etc. It's essential for thermal management, especially if we want to prevent overheating or blow-ups. And power is also important for cost, safety, and efficiency. All things that engineers really look at when they're trying to design the next best circuit. So if you like these types of videos, if you want me to continue doing them, please reach out to us at voltagelearning.com and make sure you subscribe, like, and follow for more content from us.